Let's review the natural log function. We use this quite a bit in calculus. Remember how we defined the natural log function? We started with the exponential function with the natural base, so e to the x. And the natural logarithm is the inverse of that. So graphically, anything we know about the function e to the x can translate over to the function natural log of x. So remember, for an inverse, graphically anyways, its relationship is a reflection along that line y equal x. So if I reflect this asymptote here out at 0 becomes an asymptote down here. And try and make that look roughly like the reflection across that line. That's what our natural log would look like. So just from that, what do we know? Well, we know that e to the x, well, e to the 0, we do know that. E to the 0 is 1. So that tells us that over here, natural log of 1 is 0, so we know that. That's a fact we know. Comes from the fact that we know that e to the 0 is 1, so maybe the corresponding fact we're getting that from. What else do we know? E to the 1 is just e. Anything to the 1 is e, even though we're not sure exactly what that value e is. To the first power, we have e. So e to the 1 is just e, which means that natural log, reversing that process, natural log of e is 1. So somewhere over here would be e. Now, these are transcendental functions, so it gets dicey when you're in between here what these values are. And that's really where we're going to be headed with our Taylor series and such, is to find ways of computing values of these functions arbitrarily along their domains. But we're not quite there yet. What else can we say? Something we're interested in is long-run behavior. So like I mentioned previously, we know that as we head out to negative infinity, e to the x is headed down to 0. So limit-wise, that ends up meaning here on natural log, as we approach 0 from the right, the limit is negative infinity. So the limit as we approach 0 from the right of the natural log function is negative infinity. And then as we go to infinity with x, what's happening with natural log? Well, it's very slow in its growth. So if you were to graph this in a Desmos or a calculator or something, it almost looks like it's got an asymptote. But let's think about the relationships between these two functions. The x's, the things I'm plugging into natural log are the things that come out of e to the x and vice versa. So what's the biggest output that is there any cap on how high natural log can go? Well, that's equivalent to saying, is there any x value that's the highest x value I could plug into e to the x? And there's not. I can keep plugging larger and larger inputs into e to the x, which without bound, right? Billion, trillion, as high as I want to go, I can plug a number in. So that means the outputs of natural log will go as high as we want. So there is no upper bound on that. Grows very slow, but there is no upper bound. So the limit as x goes to infinity of natural log is infinity. Even if it looks asymptotic, it's not. It just grows very, very slow. It's really our logarithms are our slowest growing functions of the functions that we look at that have any growth at all. Logarithms are the slowest, while exponentials are quite fast, faster than polynomials. Okay, so we know a few values. We know some long-term behavior. What else can we say? Well, I guess back to values here. Inputs and outputs, domains and ranges. So as we see here, there's nothing from 0, negative. So the domain of our natural log function would be x greater than 0. The range, which we kind of addressed with these two limits, we go down to negative infinity, up to positive infinity. So the range is all real numbers. So our outputs range from negative infinity to positive infinity. What else can we talk about as far as the behavior? We've got the domain and range, some values. It's always increasing. Natural log is strictly increasing function. Now, something else that we will want to do sometimes to make our integrals that involve natural log easier to deal with is to apply some of those basic manipulations, those properties of logarithms. So let's review those basic properties. And that is the log of a product is just the sum of the logs. This one is really nice when you're dealing with limits. These two limits might give you something indeterminate, but together they don't. Also with division, natural log of A minus natural log of B. Same thing, you might have infinity minus infinity here, but when you put them in a ratio, you can do L'Hopital's rule or something like that. Also, natural log of A to the B is B natural log A. So those are our three properties. Those are useful to use. Also, because natural log and e to the x are inverses of each other, we have the property that natural log of e to the x. So since the outputs of e to the x become the inputs of natural log, so then the outputs of that, you're back to the inputs. In other words, they cancel each other off. Whenever you compose a function with its inverse and vice versa, e to the natural log of x equals x. Now, we got to be a little bit careful about domain and range. Make sure we're not saying anything beyond what these functions do. Natural log can only take in positive numbers, right? But this quantity, e to the x, will only ever be a positive number, so that's fine. Natural log of x, this will generate numbers greater than 0, and then we're just plugging in numbers greater than 0 into e to the x to get back to our x value. So we're fine there in those compositions. Lastly, we pretty much focus on the natural log, but if you do end up with a log of a different base, you can always change it into natural log. So by our change of base formula, the log base A of B is just natural log of B over a natural log of A. So We know how to take derivatives of natural log. You could learn a special formula for derivatives of logs of other bases, but the easiest thing to do is whenever you encounter logs of other bases, just convert them into natural logs. And for our purposes, this covers what we need. These manipulations are great when we're doing limits. These manipulations also you will see for L'Hopital's rule are nice. This is great for differentiation or integration for that matter. These limits we'll be looking at, so make sure we understand the long run behavior there. And be aware that there's only really a small group of values that we know exactly. And it's going to need some powerful approximation techniques that we'll look at later on to get arbitrary values of natural log or e to the x for that matter.